Okay, I think I will start the class. just a minute.
בסדר?
לא בסדר.
בגוגל מיט, אבל כן זה מקליט וכן זה מצלם.
כן?
כן.
100%, תודה. ביי. Okay, so today we are going to talk about something else. This is an auxiliary topic that deserves probably more than one week, but we don't have the time. And that is about the Dirac equation. I remind you when we started the course, I told you that there are several things that this course is going to expand over what you learned from undergraduate quantum mechanics. The first one was how to deal with many particle systems, and that's basically all we've done up till now for 12 weeks. The other issue was if we even focus on only one particle, the quantum mechanics that you learned so far use the Schrödinger equation as the framework, right? And the problem is that the Schrödinger equation, I don't know if you remember this from your undergraduate, but let me remind you. You know, the quantum mechanics was developed by several people, layer by layer, and at some point it was recognized that you need a framework to describe quantum particles, which involves some mathematical structure, and that it should be something that accounts for the fact that you have uncertainty, that you have particles that behave also like waves and vice versa, the particle-wave duality. All that was framed by Schrödinger in terms of his Schrödinger equation. But he noticed that to write his equation, he needed to make an assumption. And today I'm going to tell you first what was the problem, why did he have to make an assumption. And the assumption was that the particles are not relativistic, that the velocities are typically much smaller than the velocity of light. Now, since the main motivation was to explain electrons and atoms, when, that was one of the purposes, because there was the Bohr model for the atom, and this was one of the first concrete quantum mechanical problem that needed solving. So electrons in the atom their typical velocities are not so large. So it wasn't an issue to ask what happens if you accelerate electrons to near speed of light, okay? Nowadays, since, much before now, but much before that, we know that particles can get to relativistic velocities. You see relativistic effects in the lab. And the question is how to extend the Schrödinger equation to relativistic particles. So that was what Dirac did, and the extension is not trivial, okay? So let me first explain why there is a problem, okay? So I remind you what is the quantum mechanics that you know. Schrödinger equation has the following form. You have a differential equation, okay, which is of this form, right? And here H is, let's now talk about the free particle, okay? Of course you can always add potential, but for free particles, H is p squared over 2m. M is the mass of the particle, and since this p is an operator, and Schrödinger presented it as a differential operator. Okay, it's a gradient operator. So therefore, this becomes nabla square, and so on. Okay, and the solution of this equation is a wave function, and the question was, what is the interpretation of the wave function? And as you might know or might remember from your undergraduate, this was an issue that was studied by several people and had various interpretations, but the accepted framework, which we always work with, is that the physical significance of the wave function, it's not something you can measure directly. You cannot measure a wave function. What you can measure is first of all, expectation values of physical operators, or you can measure the probability of a particle to be in place and time. Okay, so you are associating a probability density function of space and time, which is the square of psi. Okay, so by the way, I just remind you that this psi in the Schrödinger equation that is written in the real space basis, the wave function is a function of space and time in general, and you can also get the static version if you assume solutions that that replace this time derivative operator by a constant, right? So that gives you energy eigenstates, and that's the static Schrödinger equation. But let us think of the time dependent. That's really the basic. It's a differential equation with a first derivative in time and second derivative in space. Okay, and its solutions are complex functions, but the absolute value square, which is a positive definite quantity, has physical meaning. It really is, if you can measure it, like measuring clicks on a screen, doing the statistics, you can really measure it and quantify what is the probability for the particle to be at a certain position at a certain time. Okay? So there is an additional property of this probability density function that, and I think you have proved it in your undergraduate, at least if you learned the course with me, because I remember teaching it. I don't know if anybody remembers. You can show that from the Schrödinger equation, you can get a continuity equation which settles or if you like, it nails down the fact that this probabilistic function really has a meaning, okay? Because if it's a probability, it's something that has to be conserved. There's a conservation of probabilities. And the conservation law is represented by this continuity equation, right? Where rho is probability density, and J, which is also some combination of the psions, the space derivative, is a probability curve. Okay? So now, how does this continuity equation follows from Schrödinger? Anybody remember how we do the calculation? What is the trick? So the Schrödinger equation gives you time derivative of psi equals something. And I'm not doing the calculation, just reminding. If you multiply it from the left by psi star, you get, and do of course the same thing for both sides, and then you take the complex conjugate of this equation and multiply by psi on the other side. If you add up the two equations, you get a continuity equation. Okay, it just follows from the fact that d rho, time derivative of rho is time derivative of psi star psi, which is just doing the usual rule. Okay, that's where it comes from. Okay. Okay, great. So why am I mentioning it? It's very important because if you want to have a consistent theory that describes quantum mechanics in terms of mathematical objects, and eventually you want to assign them with a physical meaning, then you must have a probability density that is positive, definite, and that satisfies a continuity equation. Otherwise, you have a problem, okay? And that's exactly, we'll see in a minute, what happens if we try to generalize this idea to relativistic particles. So what is the problem with this? Why is it not describing relativistic particles? That's because the kinetic energy is an approximation of the more general dispersion between energy and momentum, which is the following. So the general dispersion is that the energy is, okay, now I'm using here units where h bar and c are 1, okay? Until otherwise noted. So I'm erasing all the c. So in these units, energy, mass, frequency, and they all have the same units. Okay. So this is the correct energy dispersion, and therefore, if I want to, now if I want to write an equation like this, I want to just replace to replace the operator h by something that should equal the energy. Okay. Then so I'm just looking at the static equation, right? So I now want to substitute for h this square root of p squared plus m squared. Now that's a problem. Why? Because p is, and I still want p to be this differential operator. I mean, that's what we discovered explains the behavior of the correct way of describing the free particle, right? That's the physical meaning of the or the mathematical representation of the momentum operator is a gradient. So this is not mathematically kosher operator, right? A square root of an operator, of any operator. Okay, now forget about the gradient. Okay, the square root of an operator does nothing like it. Okay, it's not mathematically well defined. Okay, but you can say, okay, so the Hamiltonian itself is not a well-defined operator, but if I square it, I get something valid, okay? So let's take the square of this instead. I'm looking for solutions to, so this now will be, let's identify this with h squared, but that's a well-defined operator, there's no problem with it. But then what it means is that the left-hand side, which is the energy square, if I want to go back to the time-dependent equation, it will be a second derivative, right? Okay, so, and in fact, this gives you, if I'm writing an equation like this, so let me write it here, minus, okay, h bar equals 1, so this is just psi equals this h squared. Okay, so I'm looking for solutions to such an equation, and if I move this operator to the left-hand side, or vice versa, I get an equation that has the following form, and I'm writing here as a relativistic notation that has space-time, one time component and 3 space, and then the second derivative can be written as, write it like this, minus m squared. Okay, so this is the equation you get. Well, let me define what is the meaning of this differential operator. When I'm writing it with these indices, remember this is actually summing over all mu, where mu is 0, 1, 2, 3, if you have a 3-dimensional space. And the mu, this is actually minus, okay, yeah, and this is again with units c equal 1, okay, otherwise you have the factors of c squared. Okay, that's just the definition of the differential, okay? Okay, this is a very nice and simple wave equation. In fact, you know this equation, you saw it many times, right? This is just nothing but the free wave equation that you get for phonons, for photons, etc. And it's actually called the Klein-Gordon. So this equation is good, but now we have to ask ourselves, can it describe a relativistic particle? Okay, so you know this equation comes in physical situations that we know and we've seen in this course as well, in connection with, for example, a wave equation for the displacement field of elastic medium, or for the electromagnetic field. But in all those examples, the field for which you solve was not a wave function of a particle, okay? It was something else, with some kind of a collective degree of freedom. And that's not what we want, okay? So I emphasize that this equation is, of course, a good description for wave phenomena, but not for a wave function. A wave function of a particle is something that should have this meaning, okay? Okay, so it can be, generally, it is a complex function of space and time that its physical significance should be associated with a probability, and this probability density is if I write it more explicitly, psi star psi, okay, a positive definite thing that satisfies continuity equation and so on. So now let us see there are actually two problems with the Klein-Gordon equation as it is. The first problem, which is in fact not the most problematic one, is it's an equation not for the energy, but for the energy squared, for the Hamiltonian squared. And the left-hand side, if we look at the static version, the left-hand side has an eigenvalue E squared. This is always positive, but it's the square of the energy. So if we ask ourselves what is the spectrum will have positive and negative solutions. Okay? And negative solutions, and for free particles, these negative solutions are not bounded by anything. That may be a problem because there is no ground state. Okay, it's not bounded from below. That's a problem we can actually solve, but I will tell you at the end of today's class, we'll get to it, okay? So that's not the problem, yeah, sorry?
What's the meaning of the ground state if we were talking about free particles, not bounded?
Free particles, like the free particles that are described by Schrödinger equation, they have a ground state. The ground state is zero momentum. That's a ground state, right? The energy spectrum.
Is that the same for the particles that have negative energy too?
No, because the energy of that's exactly the thing. The kinetic energy of a non-relativistic particle is positive definite, right? It's p squared over 2m. So the momentum can have the momentum is a vector. So in any case, it can be have negative values in any direction. But the energy has a ground state. Okay. Okay. So very simple. So a particle in zero momentum is the ground state. Okay. But if the energy can be negative, there is no ground state, and but we'll come back to it because that's not an issue. That's an issue we can understand, and that was part of Dirac's ingenuity. Because in his equation there is also an E squared, right? There are negative solutions, but it doesn't have this form. This is not kosher. Why is this not kosher?
Because
and that has to do with this probability density thing.
You have a second time derivative.
Yeah, sorry?
You have a second time derivative, which
exactly.
is writing as a continuity equation.
That's exactly right. So if I want to do the same trick I did with the Schrödinger equation and to convert it into a continuity equation, I discovered that by the way, I should also mention something that even if I have not a free particle, but I add a potential, any potential, arbitrary potential energy, this continuity equation is still there. Okay, so it's a very powerful statement. Okay, there's this probability, this continuity equation always comes in and does not depend on the potential. Okay? So, but here we cannot do it exactly as you say because of the second derivative, because to make sense of, to convert it into something that will give us the continuity equation, we must admit a rho that has the form of something like this, okay? So something like this will serve as the probability density. I mean, this is something that if I take the time derivative will give me the equation, and that's not kosher because this is not a positive definite object, and it cannot have the physical meaning of a probability density. Okay? So we have a big problem, and nevertheless, we know, so that there is a very strong constraint. We know that this dispersion, this connection between energy and momentum must be obeyed. That's the relativistic dynamics, okay? So the conclusion is, or what Dirac realized is that if we think of the Schrödinger equation as a straightforward generalization, namely where this psi is some scalar function of R and T, it cannot work. We cannot make it work. Okay? How can we overcome this difficulty? So Dirac pointed out that let us assume that this psi, it is also a function of R and T, but it also lives in another independent space, and it's not a scalar, it's a vector of some kind, or something that is what now we would call a spinor, okay? So it's a more complicated object, it's a vector. Anyway, we know that wave functions in general are vectors, right, in some Hilbert space. So we keep the R and T dependence, but we also assume that this psi is not just a scalar, but it has components, okay? At the moment, we don't know what is the structure, what is the space, why, what, okay? But let us just think about it mathematically. We want to write something that is mathematically well defined, okay? Okay, so let us see what can be done to give us what we want. So instead of writing a Hamiltonian that is something like a square root of something which is not well defined, not kosher, let us assume that so what I'm writing here is a guess, okay? It's a guess for a form of Hamiltonian that will give us what we want, and it is the following. I'm writing it as, first of all, we know that it is an operator, and an operator can be written as a combination of operators, but if we think of the space coordinates, the vector P is an operator, but it also has 3 components, if it's in 3 dimensions. So when I'm writing this, both alpha and P are operators. And Actually, let me put here a hat just to clarify. But each of them have 3 components, okay? And then we add something which will account for the mass. We multiply it by another operator that has only 1 component, beta we call it at the moment. And m is just a number, it's a parameter. That's the mass, the rest mass of a particle, if you like. Okay? So this is what we guess, and the idea is the following, that, so first of all, the time-dependent Schrödinger equation will still be of the form a first-time derivative in time, okay? That will solve the problem with the probability and all that. But this H assumes a slightly more structure, and the idea is that while P is still the differential operator that we all know and love, these alpha and beta, which are in fact, alpha is a combination of three components, and each of them is an operator. And alpha, 1, 2, 3, and beta are operators in some space, okay? And let us, for simplicity, assume that it's some kind of a discrete space. It's not space, it's something that is not related to to space and time, okay? So it's in a different dimension, okay? It's an independent degree of freedom. Okay, so we assume this form without knowing what are alphas and betas, and we assume that with this Hamiltonian, one should satisfy a time-dependent Schrödinger equation in this form. But we also know that if we square it, we should get the dispersion of the relativistic particle, okay? So let us assume that there are solutions of free particles which have energy E and momentum P, and P now is going to be a quantum number, okay, related to a wave vector. So in this basis, I would like to see that this is the correct dispersion. So if I plug in this Hamiltonian in the time-dependent Schrödinger equation and assume that the wave function has a time dependence that is just e to the I et, okay? Then I get the static, okay? This is the static Schrödinger equation, not Schrödinger, static Dirac equation now. But now I know that in order to see this dispersion, I want to be able to show that E square minus P square minus M square times psi equals 0, okay? So, in other words, I want to see that if I plug in this H here, and I square the right-hand side of the equation, I will satisfy this result, okay? So somehow the alphas and betas should disappear when I square, okay? Now, if you do the algebra, Okay, so what I'm saying is that what I want is that alpha p. Let me not write I'm not writing the hats all the time because there are too many of them, but let us remember that alpha and beta are all operators, and of course p as well. So what I want to say is if I take this and I square it, namely I just multiply it by itself, okay, then this should give me p squared plus, p squared plus m squared, okay? That's what I want to prove. I want to demand it, okay? I want to demand it. And it turns out if for that to be satisfied, you need to require something of the alphas and betas. What is this something? So it gives an algebra. First of all, for this to be satisfied, you must obey that alpha j squared and beta squared are just one, okay? The identity, okay? And here j is 1, 2, 3, or x, y, z, okay? So for any j, and this has to be satisfied, so the square of these operators has to be 1. So the other thing you find out that you need to satisfy is that alpha k, alpha l, well, k and l are one of those, is delta k. And another thing, for any j, this is 0. Well, these curly brackets are familiar to you, I think. These are the anti-commutators. Okay, in other words, alpha k, alpha l is equal to minus alpha l, alpha k if l is different from k. Okay? And if it is the same, then you're back to here and it should be 1. Okay, so this is the property of these operators. They have to be mutually anti-commuting. Okay? I mean, if they were, okay, so they have to be mutually anti-commuting and their squares are 1. What does it remind you of? Or if you can, what?
Fermions.
It reminds of fermions, but let us think, since we are heading at writing the Hamiltonian as an operator in some basis that has discrete components, it's better to think of some kind of matrices.
Clifford
Matrix
algebra.
objects.
Clifford algebra.
Clifford, you said? Well, it's so actually they are the Pauli matrices. The Pauli matrices have this property. Okay, if you think of 2 by 2 matrices. Okay. So that's it's very tempting to say, that these are Pauli matrices. But if we are thinking of particles so by the way, if the particle would live in 2 dimensions, then that's the answer. Then you conclude that one can write a Dirac equation with which has a one-time component and 2 space components, and there are 3, as you know, there are 3 Pauli matrices. Okay, so I'm reminding the Pauli matrices for the spin operator. I'm writing them down here. This is sigma 1 or sigma x, as we sometimes call it. This is sigma 2, and sigma 3 is 1 minus 1 is diagonal. Okay, and that's for a spin half particle. We have the 3 Pauli matrices, okay, and any Hermitian matrix 2 by 2 can be written as some linear combination of these 3 Pauli matrices, and together with the identity matrix, sometimes it's denoted C sigma naught, which is just the identity, okay? So if we had particle in two space dimensions, we would conclude that one can write a Dirac equation where the wave function is a spin half 2 components. And that would be wonderful because we actually know that, for example, fermions, electrons, and actually any fermion of the type of the matter particles that we know, protons and neutrons and electrons, they all are spin half particles, so they have a spin. So that's great. I mean, that would suggest that that fermions, it can work for fermions, but we have a problem if we want to extend it to the 3-dimensional space, because in 3 dimensions you cannot have 4. So here we need 4 distinct non-trivial matrices, okay? Beta and 3 alphas, okay? So the Pauli matrices are not good, are not enough, okay? We need operators in a bigger space, bigger dimension space. So, okay, but they are kind of like Pauli matrices, okay? So how can we extend it to a higher space and still maintain the structure that is very much reminiscent? Let us assume that we have a space that is not 2 by 2, but it has 4 components. And what are these 4 components? You can think of them as spin, sigma, and another degree of freedom that is like an isospin, okay? And it also has its Pauli matrices, and let us denote them by tau, okay? Now, what are they? No idea at the moment. We'll come to that later, okay? Because it's a kind of prediction. If it's true that that's what you need, maybe it has a physical meaning, okay? So it turns out that's what eventually give us the final version of the Dirac equation. Basically, okay, so let me erase this, write it down. And just remember that the Pauli matrices, in fact, obey this anti-commutativity.
Except for gamma for 0.
Except for 0. 0 is the identity, yeah. So it commutes with everything. That's right. Yeah, so that's why it's not another, right? So we only have 3. Okay? Yeah, and here that's exactly the point we need. So this is satisfied only among the three Pauli matrices, but let us assume that there is also another spin half-like degree of freedom with Pauli matrices that I denote by tau. So tau j, tau k are also anti-commuting, and in fact there is so we also have other rules for, so the Pauli matrices certainly obey this, but they also have the following relation between them. There's an algebra. Let me just remind. So sigma j is there a factor? Sorry. Oh, it's fine. So it's minus I sigma k sigma L, where here the order is cyclic, so okay, let me write it like this. So it's minus I epsilon j k L sigma k sigma L. Okay, that's the relation between each Pauli matrices to the other. Okay, that's a spin algebra, spin half algebra. Okay. Okay, so we have this for the sigmas and also for the taus, the same thing, it's the same structure. And now I want to use them to build a four-dimensional space. So I define here a basis of 4 states. Okay, so what our wave function psi is going to be a spinor in a 4-dimensional space, so also so-called 4 spinor. Okay, so this is what it is. It's going to be psi 1, psi 2, psi 3, psi 4, where each of these is a function of RNT. Okay, that's how the wave function look like, and the basis here is let me write it like this. So 1 is that both tau and sigma are up. 2 is spin down, but tau also up, and 3 is plus minus, and 4 is minus minus. Okay, that's the basis.
What is tau again?
Tau is another degree of freedom that is like a spin. Okay? Okay? Now, so for example, if I have a wave function that look like this, it has 1, 0, 1, 0. Okay? Namely, it's a superposition of only 1 and 3. Okay? So it has spin up. Okay, so how do I see that it has spin up? This is like the spin of the spin is up, and this as well. Okay, but in the tau basis, so this is this component is so let me actually maybe explain this. So what I mean by this is the first, this pair of components and this pair of components belong to the tau. So tau plus is anything that has 0 here and something here. Okay. Now this something can be either 1, 0 or 0, 1. And that's the difference between 1 and 2. Okay, for example. Okay? So altogether, let me then tell you what is. Now we can choose. So we can choose various choices for the alphas and beta, such that they will satisfy the requirements. Notice, by the way, that they are all equivalent, right? Because I have here a freedom. Anything that satisfies the constraint, okay? Namely that this equation leads to this dispersion and that forces the alphas to have anti-commutators and all that. Any choice is legitimate. So we can change basis according to convenience for various problems, and I'll give you examples. But let me just mention one that is a possibility. So it turns out, and that's something you can do a simple algebra and check. If I define the alpha j's to be tau 1 cross sigma j, okay, sigma j, and beta I choose to be tau 3 cross sigma naught, where sigma naught is just the identity matrix. Then you can convince yourself, just do the algebra, that they obey all the rules, okay? So again, what we require is that alpha j, alpha k are jk for any jk different from 0, any jk, and alpha j beta is 0, and also beta square is 1. Okay, that's what we require. So now let me explain what it is. Okay, I'm writing it schematically, but let's write it as a 4x4 matrix, because then it becomes clear what I mean by tau and sigma. Okay, or tau or sigma. So alpha j has the following structure. First, I have the tau 1. You can think of it as these blocks. And tau 1, what is tau 1? Tau 1 has 0 here, 0 here, and here it has 1 and 1. Okay? So that means that whatever I put here is the same. So these components are symmetric, but the block here, each of these blocks is itself a 2x2 in the spin. Okay? So this is actually sigma j, sigma j. Okay, and that's the structure of alpha, and then beta is write it like this. So it's sigma naught and minus sigma naught, where sigma naught is actually the identity matrix, and here I have 0. So it's block diagonal, and in fact it's actually diagonal. Okay, so it's 1 1 minus 1 minus 1. So this is a convenient basis in the sense that it's the term that couples to the mass m is diagonal, and this is completely off diagonal, but it involves the spin. Okay. Okay. So that's this is a one representation, but that's not how Dirac wrote the final Dirac equation as we know it. what he did is the following. There is one slight inconvenience here, if you like, that we separate the alphas from a beta. Okay? Let's try to have a structure that is more symmetric. It has 4 objects that obey a mutual algebra, and it's just one set, just like the Pauli matrices for the case of the case that we need only 3. We have only one equation that defines them all, right? So I want something like that for these new 4x4 matrices, and the choice is something that is called gamma matrices. Okay, so this is what they are, and let me define gamma mu. Again, mu is a relativistic index of a 4 vector. There is a gamma naught and a gamma vector, where gamma vector is a 3 space component, 3 component, okay? So it's a 4 vector, but each component of this vector is a matrix, a 4x4 matrix, an operator, okay? So this is what they are, and I define them from the alpha and beta of before. I want to define them in such a way that gamma naught is actually nothing but beta. It's another name for beta. And gamma vector will be beta alpha vector, where alpha is the alpha of before. Okay? Very good. Now, why is this definition convenient? Because now I can write just one anti-commutator relation, which is obeyed for any of the 4 components, mu and mu. So the anti-commutator, in fact, all of them are mutually anti-commuting, and they can be written. So this is the identity times a metric G mu nu, where G 0, 0 is 1, and G J J for any J 1 to 3 is -1. Okay, and for any mu different from mu, J mu nu is 0. Okay, so it's diagonal. Okay, and it has this structure. Okay, so this is a mathematical property that these gammas obey. But within this specification, you can still find different representations of the gammas. Okay? So you have a freedom, and let me write one that is common in the literature. And all the time I'm using this basis, okay? The basis of the 1 to 3 with the sigma and the tau. Okay, this can be erased. This we also don't need anymore. Okay, so all the time. Okay, So, yeah, so let me write the following. First, gamma naught. Gamma naught is just what before we called beta. So it has the identity, 2 by 2 identity, and minus the identity, and so it's diagonal. Okay, this is again diagonal, and then we have the gamma j, where j is 1, 2, 3, and that is given by again it's an off diagonal, but now it's so before, remember, for the alphas had the sigma j, but now this gamma j are beta times alpha, so it changes the sign of the other block, and that's why you have a minus, okay? So this is what it is. This is a representation. And then there is, it is useful also to define a fifth gamma matrix, which it doesn't appear by itself in the Dirac equation, but can be used as to make transformations. So if, for example, you want to rotate the basis, it's useful to do it with this gamma phi, and its definition is I times just the product of all the others. Okay, this is its definition. Okay, times I, a factor of I, and if you do the algebra for our case, okay, and use the algebra of the Pauli matrices, you find that in this basis, gamma 5 is going to be off diagonal, but on the off diagonal you have the identity. Okay, that's what comes out. Okay, so that's what it is, and now let us go back to the Dirac equation that in the beginning, let me rewrite it in terms of alpha and beta, and then we'll do the conversion to get the gammas. Okay, so that's the Dirac equation, or the equation we got before was it was alpha dot p plus beta m, but now in order to get to represent it with the gammas, what I do is to multiply the equation from the left by the matrix beta. Okay, so I put, let me do it with a color. I put here beta. Okay, and beta, again, it's an operator acting on psi. Okay, so it's a matrix acting on the spin of psi, and we have to put it here as well. Okay, I multiplied both sides, but now you see that on the left-hand side, the beta will remain. Okay, and it will appear as a factor of gamma naught, because beta is gamma naught. But on the right-hand side, beta alpha is now just gamma vector, and beta square is 1. Okay, so altogether, we are going to get the following equation. Let me write it like this. So I'm getting that. Sorry. Yeah. I gamma naught dt. And now I move this side of the equation to the left hand side. Minus gamma vector times p. But what is p? P is minus I gradient, okay, right? For h bar equal 1, minus m. All that multiplying psi will give you 0. Okay? Now, I can rewrite it so that the minus minus here cancels, and I get something that I can write more compactly as I gamma mu d mu minus m equals 0. And that's the canonical form of the Dirac equation. All right? And I also want to introduce a common notation. And here mu is again 0, 1, 2, 3 for vector. This is a relativistic expression that just means, so this is gamma naught dt plus gamma, okay, this is what it is, right? Okay, and there is also a notation in the literature, gamma mu d mu can be written as, in a short-handed notation, as differential with a slash. If you look at, I don't know, all these t-shirts with the standard model, you see this notation, okay, in high energy physics of the standard model. Okay. Good, so that's the Dirac equation. We'll discuss some solutions and what it means, but we are not really done here because we want to convince ourselves that all of this makes sense in terms of this idea of wave function as something that if you square it, you get the probability, the continuity equation, all this stuff, okay? In order to be able to prove it, we have to look at the conjugate of this equation. That was part of the proof, how we got the continuity equation from Schrödinger. We want to do the same for Dirac, okay? And once again, it's not entirely trivial. Now remember that this psi is not just a complex function, it's a vector in this four-dimensional space, and each component is itself a complex number, okay? Or actually a complex function of space and time in general, okay? So, so we need to do the conjugation carefully. I think this I can erase for now. Okay. All right. So the conjugate Dirac equation is, let me just repeat it here. This is the equation itself. the conjugate equation is, first there is minus I, right? Because you do a conjugation.
But doesn't it cancel out with the derivative?
What concept?
Because it's a first derivative. First derivatives should cancel out.
Why? I don't understand what you mean by cancel. I mean,
The minus I should cancel out with
If you
first
you
two.
make the sum of the two equation, the derivative will cancel.
I'm not. I'm writing. I'm now going to write the equation.
Okay.
I didn't write the equation. I'm not yet doing a sum of anything. Okay. Let me just first write the equation. Okay. And so this is. I'm just writing what it is. So now you have. So I have to now. It's a Hermitian conjugate, so I have to change the order of the gamma and the psi and write it as a derivative of psi dagger. Okay, psi dagger is if psi was a 4-component vector, psi dagger is psi 1, psi 2, it's a row vector whose components are the complex conjugates of.
Shouldn't the dagger be outside of the parentheses?
No. So the dagger, that's what it is, but the derivative acts on it, okay, and it has gamma. So the derivative acts on the space-time components of this. This is what it means, and this is gamma. And I forgot to say something important about these gammas. So this is gamma mu dagger. Okay. Now, so if you remember for the Pauli matrices. The dagger, sigma dagger is equal to sigma, right? It's they are Hermitian. The gammas are not Hermitian. Okay, so that's one slight complication that we get from extending it to a 4-dimensional space. So I forgot to mention, but let's just first finish writing it. This is the conjugate equation, right? And now why am I not writing gamma mu? Because gamma mu dagger is not necessarily equal to gamma mu. Actually, now I'm sorry that I erased, because you could see, so in the representation that I wrote before, we had, let me just make sure what it was again. So it was gamma naught was this, okay, and gamma j was sigma j minus sigma j, and the Pauli matrices are all Hermitian. So what can we say about gamma j? That it's actually anti-Hermitian, right? So and that's actually true in any representation. So gamma 0 dagger equals gamma naught. That's Hermitian, but gamma j dagger is anti-Hermitian. Okay, and we can, however, represent gamma j Hermitian with gamma j itself as follows. You notice that if I do a transformation, if I use gamma naught as a transformation and then I multiply from both sides, I get back gamma j. So this is what I get. So gamma j dagger can be related to gamma j by multiplication by gamma naught from either side. Okay? That corrects the anti-hermiticity. Okay? Now, actually, this relation is trivially also correct for gamma naught, right? Because gamma naught is anyway Hermitian. If I multiply it by gamma naught square is 1. So I can actually write, instead of separating, I can write the following more general requirement, which is that gamma mu dagger is gamma naught, gamma mu, gamma naught for any mu. Okay? This is generally correct. Okay? Okay, so now with that in mind, let us rewrite the conjugate equation
We can also,
using this, yeah,
we
sorry?
can also do it for the identity, can't we? And simplify it even further.
Of course, you can always replace the identity. We'll do it in a second.
Because then
But
we can just drop it.
what
to
I'm
this.
saying is that this relation, this identity, is correct for any mu,
Yeah.
including mu equals 0.
Yeah.
Okay. Okay. Now, let me now use this, because now I can rewrite this as minus I d mu psi dagger, and then instead of gamma mu dagger, I can write gamma naught, gamma mu, gamma naught minus m psi dagger equals 0. Okay? Why did I do this? Because now here's what you can do. Let me now take this equation and multiply it from the right hand side by another factor of gamma naught. Okay? Okay, in the first sight it looks like it will complicate things, but we'll soon see that it will give something really, really nice. So this will result minus I d mu psi dagger, and now we have gamma naught. Actually, I don't need to write this, but we understand what I mean. Gamma naught, gamma mu, gamma, and now gamma naught square is 1. Okay, so I can erase this. Okay? Minus psi dagger gamma naught. Sorry, I forgot the mass. Yeah, so m psi dagger gamma naught. Okay. Okay, what did I gain? It looks like I eliminated one factor, but then it came to haunt me from the other side. Okay, but what you see here that in both terms in the equation, I have a combination of psi dagger and gamma naught. Okay, so which is a row vector which I can define. Let me now write a definition. Okay, this. This is a definition of something that I denote by psi bar. Okay? So it's not just the conjugate, it's conjugate with this correction. Okay, under this definition, I get the conjugate of So let me write it, minus I, d mu psi bar gamma mu minus m psi bar equals 0. Okay, so this is now is going to be an equation for psi bar. And this equation has the same structure as the Dirac equation itself, which is gamma mu d mu psi minus m psi. So these are the two conjugate equations I want to work with. And why do I write it like this? Because I want now to repeat the trick of defining probability density in such a way that somehow the combination of these equations will give me a continuity equation. Okay? And you can see that in fact you can do it in exactly the same way as you did in the Schrödinger equation, by multiplying this from the left by psi bar and this from the right by psi and combining them. And let's not do the algebra, just see what you get is the following. First of all, if I take again these coupled equations and now define something that I call J mu. It's a generalized or 4-vector current, probability current. I define it as psi bar gamma mu psi. Okay. So, and mu here is again, it's 0, 1, 2, 3, it's 4 vector. This is a probability, I'm claiming that this is a probability current. Why? Because if I manipulate these two equations, just as we said, you can see that you obtain a continuity equation. That's exactly what it is. Okay? All right, so let's put this in a box. It's a very important result. Good, so first of all, I say the following. I can define, you can say, but we're not done yet, because I can always define something that will look like it obeys a continuity. Not always, but let's convince ourselves that this is really physically describing exactly the same thing that we got for the non-relativistic particle. So obviously this is a continuity equation, right? Because it's the time derivative of J naught is going to be the probability density, okay? So, in other words, this J mu, if I write it as a 4 vector, it's rho, and actually it should be, to be in the relativistic 4 vector notation, should be minus J, okay? And that will give us what we want, but the J0 is rho, okay? Let's convince ourselves that it is really a probability density. It has to be positive definite. Okay, that's the requirement. So what is it? It's psi bar gamma naught psi bar. Psi, okay? But let us remind ourselves what is psi bar. Psi bar is psi dagger with a gamma naught. So if I plug it in here, I get gamma naught squared. But gamma naught squared is 1, right? So this is nothing but psi dagger psi. What is psi dagger psi? It is just a sum over the components from 0 to 3 of psi mu absolute value square, because remember this is psi dagger, this is psi, and what you get is just the sum of the square of the components. Wonderful. This is just what we like. It's really the probability density of function, and if it's normalized, it's going to give you something that has a total of 1, and this is positive effect. Okay? So it's a legitimate, so whatever this force spinor is, it obeys everything you like. It gives you an equation that, let us summarize what it gives. First, it gives you the correct dispersion, okay? And in fact, you can find free particle solutions with a well-defined momentum P related to some wave vector and a well-defined energy E that obey the relativistic dispersion, E squared equals m squared plus p squared. Secondly, it gives a differential equation where all the algebra is consistent, okay? Everything is written in terms of well-defined operators, and it gives the continuity equation. The wave function we get can be interpreted in exactly the same way as we know from childhood or from non-relativistic one. Okay, so maybe it's almost the perfect time to stop. But the question now remains: what is this for? Why force spinor? So first of all, when I say particle, a quantum particle, we know that there are various particles. There are electrons, protons, neutrons. We know there are also neutrinos, and there are also photons, and there are bosons, fermions. It looks like at least one of these spin half degrees of freedom we can account for, because we know that for fermions, we have a spin, and it's a spin half. Okay. Actually, more generally, we know that fermions should have not necessarily spin half, but the spin, I forgot the English word for this, but even something that is an even number of components and not odd. Okay, so spin half or 3 half or 5 halves. So generally, fermionic particles should have an even spin. Okay, so this suggests now we need to have 4, and so it suggests that if anything, this works for fermions. Okay, for bosons, actually such an equation will have problems, but for bosons, in order, for example, to describe a photon, the photon particle, then the free equation is not good. Okay, that you have to keep in mind. The free wave, the Klein-Gordon, is a good wave equation for the electromagnetic field. It does not describe a free single photon. Okay, a single photon is okay. So it has a problem, and the problem has to do with the fact that it has negative energy solutions. But For fermions it can work. At the moment we don't know what is the other degree of freedom, because okay, spin, there is spin. We know there was the Stern-Gerlach experiment, showed that there is a spin half. But apparently there is a meaning to the other component, and discuss it after the break. Okay? Okay.
Isn't the problem not specifically that there's negative energy, but that the energy can fall into negative? Or really?
Okay, so maybe before we take a break, let me make a comment about why this problem, this sort of can be come over for fermions, okay? So, and this is what Dirac said. What actually the Dirac equation gives you, we didn't do the solution, but I can already tell you the punchline. If you look for solutions of a free particle with well-defined energy and momentum, you find that there are indeed positive and negative solutions, and the spectrum looks like this. So you have, if this is zero energy, the vacuum, let's say, then first of all there is a threshold. There's a threshold M, okay, where it's like a gap, energy gap. The spectrum starts from here, and you get positive, a continuum, right? In the infinite space, you have continuum of positive energy and a completely symmetric continuum of negative energies. Okay? Okay? And this has no bottom. Okay? It's bottomless, no ground state. But now what Dirac said was the following. That was, it created some uneasiness in the community, and in fact, there were attempts made by Ettore Majorana to invent another formulation of the relativistic particles that does not have negative energy solution, but the price he paid is that he had to assume that these particles are funny things. They're not fermions, they're so-called Majorana fermions, and okay. Which, okay, in condensed matter now we claim that we find them all over the place. Okay, not really, but this is the dream. But it's not clear if there exist for elementary particles. To this day, it is an open question whether some particles like the neutrinos are Majorana particles. But let's put this aside. What Dirac suggested is the following solution. Okay, we know that the Dirac equation works for fermions. Okay, now fermions, what is the ground state of fermions? Because of the Pauli exclusion, let's think about it as a many-body. Let's think of the world, the universe, as a many-body problem, where the vacuum that we think is not really empty. The vacuum is a state where all the negative energy solutions are filled. Okay? Now actually, now that we know, coming from solid state physics, this is how we think of semiconductors, right? There is a balance
He based
there.
it off of the electron hole theory, right?
What?
Didn't he base the Direxia off the electron hole theory, if I'm not mistaken?
No, you mean the equation was, again, it was derived by following mathematical constraints that will give a consistent theory, but the result of it was very profound, because in order to settle how physically we can imagine, how can we accept the fact that there are negative energy solutions, the way to accept them is to say, oh, they are there, but they are field states, and because they are field states, there's no way a particle can decay to them because they're occupied, right? So that's the problem. If there were bosons, a boson could go down in energy and go to, there's no bottom, so that's a pathology. For fermions, there's no pathology because the states are blocked. So there's no problem. The vacuum is a state where all the negative are filled and the positive are empty. Okay? Now, you can create a particle from the vacuum. What do you need for that? You need a threshold of energy given by the mass. And you can get this energy from an energetic photon, a gamma ray with enough energy can create a particle. But how can it create a particle? What it actually does is to promote a particle from the negative sector, just like in semiconductors, the valence band introduction. So a photon can excite, let's say, an electron from negative to positive, if it has a 2m, and what you will get is not one. You will not get one fermion, you'll get an electron and a positron. So that's what he predicted. He predicted that there are antiparticles, essentially, that actually at the time it was proven for any fermion, but the same can be argued for bosons in a different way. That any particle should have an antiparticle, and the first antiparticle that was indeed found in the lab was the positron. Okay? So it was actually predicted, and only because it has this structure. Okay, and then after the break I will say a bit more about this, okay? Okay. continue. Okay, so now the first thing I want to show next is what happens. So suppose our wave functions describe particles with a charge. Okay, let's say electron. We want to know how the behavior is modified, the structure of the equation is modified in an electromagnetic field, okay, which the particle couples to a charge E. So there is an electromagnetic field and it's described by a 4-vector vector potential, which has electrostatic potential and a vector potential, and we know that electric field is minus mod phi, magnetic field is the kernel of A, okay, that's but we know that just in the Schrödinger equation, to describe the coupling to the electromagnetic field, we do it through the Hamiltonian by generally doing the following transformation. So if we had a momentum p mu, okay, the momentum p mu transforms into p mu minus E times a mu, right? So this is how you introduce it in a...
Shouldn't there be the time derivative, or are we holding that it's static?
So no,
for
so
the,
mu has a time. So where?
For the electric field. Shouldn't there be a time derivative of the vector potential?
Ah, sorry, you're right. Yeah, that's just the electrostatic. You're right. There is actually, actually it is a curl also in the 4-vector, which gives you, that's right. Thank you. Right, that's the more general statement. Yeah, that's right. Thanks for the comment. Which is, by the way, again, a curl that involves the zero component. Okay, so the way we put it into the Schrödinger equation, if you saw it, I think, in other courses, perhaps in your undergraduate, is to replace everywhere in the kinetic energy the momentum operator with the gauge field. This is how it couples to the gauge field A mu. And here we want to do the same. But the way we wrote the Dirac equation, we don't explicitly write, so this is the momentum operator, right? The momentum operator is minus I d mu, okay? So if we use this transformation, what it means is that let me first use this to conclude that if I isolate the derivative operator, the mu is I times P, right? Just trivially. So everywhere where I have a derivative, now what happens if P goes to P minus EA? I have to replace the derivative by a correction which has I times EA, okay? So in other words, let me now define, so let me write it down here. So d mu will now go to d mu plus I EA, and this new operator, this modified derivative operator, is traditionally defined as d mu, okay, with a capital D. This is just a definition. So if I'm going back to the Dirac equation, if I want to introduce an electromagnetic field, I see that I get something I can write as exactly the same form, but the derivative is replaced by the so-called covariant derivative, and that's the one that is corrected by a charge times vector potential, okay? So that's, that describes a particle in an electromagnetic field, okay? Okay, so actually let me write it here. So this is, this derivative is called d mu, and it contains plus I A. Okay. Now let's see what happens if I do the same in the conjugate equation. Okay. So in the direct Dirac equation, I replace d mu by capital D. In this equation, I actually, one way of doing it is to just repeat the trick we did before. So we have a minus I, and now we have the gamma here. And now we plug in inside the...
Wait, no, shouldn't the gamma be on the other side? Because we're doing
What?
the conjugate.
Oh, sorry, yeah, forgot, yeah. So here so exactly, so here I have, so instead of the d mu, I'm writing now d mu gamma mu minus n psi bar. But now, if I rewrite this in terms of explicitly in terms of a mu, what I will find is minus I d mu psi bar minus, actually let me be a little careful about it. Yeah, so it's minus d mu minus sorry, something is bothering me.
Shouldn't it be plus?
Sorry. Yeah, right. So here, yeah, exactly right. So it's I E A mu psi bar mu. Okay, and then we have the masses remaining. Now let us open this, and I get minus I d mu psi bar gamma mu. Now minus I times I gives you a plus E a mu psi bar gamma mu. Okay. Now let's compare it with what I get from the from the direct Dirac equation. So it appears like, so the thing is that the term with the derivative is multiplied by a minus I, but this term is staying real, right? It has actually the same sign. Wait, no, wait. I'm getting, okay, let's first write this one, and then take the original Dirac equation and write it more carefully in terms of the operator D. So I find that there is a derivative, and then I have a minus, right? It's I times I EA, so it's minus E A mu psi. I forgot the gamma somewhere. Okay, so let's look at these two equations and compare them. Okay, this is an equation for the psi bar, and this is for psi. Now, so to go from one to another, first of all, this looks like just like a conjugate, but what you notice is that if here I had a minus E, here I have a plus E. Okay, that's how it comes out. Now, what it means is that it appears like the term that couples to the same vector potential is coupling with an opposite sign. Okay? So, in other words, the psi bar, if I want to think of psi bar as a wave function of something, of some particle, if psi was the particle, and I think of psi bar as something that represents an antiparticle, that antiparticle have to have an opposite charge. Okay? And that antiparticle is indeed just the positive in the case of elementary fermion, elementary electron, sorry, and for any fermion. Okay. Good. So now let's discuss some concrete solutions to the Dirac equation, and we are interested in free particles. Okay, so let me erase this for now, although we'll come back to it soon. Start from here. So actually now the first exercise I'm going to do will use the same representation of the gamma matrices that I wrote before, and for the time being let us ignore electromagnetic fields. We'll bring it back soon. What is a free particle solution? So just like the Schrödinger equation or any free wave equation, we have energy and momenta are good quantum numbers. So I can look for free propagating wave solutions. but now they're propagating, they have space and time dependent, and however, the wave function that we have is now a 4-component spinor. So the most general solution will be of the form, let me write it like this, psi plus minus, I want to give it an index sigma, okay, and I want to make some definitions. Let me, so I'll write it here, psi plus minus x will be, okay, there is some normalization factor. It has to do with just the volume. And then for plus minus, I will define them in a minute, times e to the minus plus I px. And now I want to make some definitions because you notice that I write x and p without the vector sign. So the definition is as follows. P is e p vector, so it's a 4 vector, okay, where the time component is energy, and x is a shortcut notation for t minus r. Okay, this is the definition. Okay, so this exponent is in fact, so for example, minus ipx are solutions of the form, okay, e to the minus ipx is e to the p vector times r minus e t. So this is the canonical form of propagating waves that you're familiar with, okay? And now, these U and V, each of them these are the two solutions. So there's the plus or minus. U is of the plus and minus is of the V. And they come with a factor of either minus IP or plus IP, okay? So now, what is E? What is E here? E is defined as positive, okay? Okay, so this E and P vector are of course related by the dispersion, okay? That's how we choose. This is why this solves the Dirac equation. It must obey the dispersion, and we define it as the positive square root, so that E is defined as positive, okay? Therefore, the minus, so psi plus is positive, it's positive energy, and psi minus is negative, okay? So actually, if you like, remember what we discussed just before the break, the positive energy solutions are the ones that describe the particles that are the electrons, okay? And the negative energies are field states in the vacuum that if I create a hole in this vacuum, that's the positron. Okay? The positron is not a negative energy particle. It's a hole in the Fermi sea that is filled by negative energy states. It's important to remember. Okay? Good. Okay, so these are the solutions, and these U's are, each of them are four component spinors. And notice that there is an index, so that there are two indices here. Plus minus for positive and negative energies, and there is also sigma, where sigma here is really the spin, up and down. Okay? So altogether, plus minus, up down, we have four distinct solutions. And it makes sense because it's a 4x4 problem. And let us plug it into the Dirac equation. So this, if you like, let's think of it as, and the other thing I wanted to say is that these spinors, U and V, depend on P vector. Okay? So the P vector is in fact the quantum number, okay? And E is dictated by P vector. All right? Good. Okay. And the nice thing is that the space-time dependence is all embedded only in this simple exponential, right? And because it's a linear differential equation, that's just plugging in the free solution, we'll get rid of the derivative, we'll replace them by factors of P and E, and we are ending up with a problem of diagonalizing a matrix, a 4x4 matrix. Okay, but it has a simple form. So let me, well, maybe not so simple, but in some approximation it can be easily solved. So if we plug it into the Dirac equation, we get the following. So it's gamma mu P mu minus M times U okay, and so this is what we get if we substitute the positive energy case. For the negative energy case, we get something similar with V. Okay? So this is for positive, and for negative we get P mu plus M. Okay? Okay, so that's a way to write it, but let us now focus on the positive energy solutions and just find solutions for the U. And we still have two solutions, right? Because U sigma is U up, U down. Yeah. Right? Okay. Let me just write this equation as a matrix, as an algebraic form, and I now define this U is a four-component spinor, and I can think of it as something that is combined from let me write it like this, okay, with an index sigma. I can write it as a two-component object where each of the component is itself a two-component speedo. Okay, so this is how it's written in the tau basis of this extra isospeed degree of freedom, but each of these is a spinor in the speed sector. Okay. All right. Now, why do I denote it by? Let me just make sure that. So let me just to be consistent with my notes, I changed the order. Let me call this B. This B, and this is S. Okay, it's a definition. Now, why did I choose the indices? The B and the S. They denote big and small. Okay, all right. For the following reason, let me now write it. I take this equation and I write it in a matrix form. So this is how it looks. It's E minus M minus E minus M U B U S, this is 1 minus, there's a, so when I'm writing this, by the way, what I mean is that it's actually the scalar times sigma naught, because this is a 4 by 4 matrix. Okay, each of the blocks here is a 2 by 2. Okay, clear? So here it's just sigma naught, and the same here. Okay, that's what I mean. And now the second term is off diagonal, and it has sigma dot p. Sigma dot p 0 and UB US, and all of this has to be 0. Sorry, here I have here a minus sign. Yeah, because it's the gamma matrix is anti-initial. Okay. Okay, this is what it is. Let me write it as two coupled equations. Okay. It's very simple. So first I have E minus M times the identity times UB minus sigma dot P US equals 0. And minus E minus M US plus sigma dot P UB equals 0. Okay, these are the coupled equations. Very good. And generally, okay, now I can plug one equation in the other and get a closed solution for US and UB, and usually they are a bit complicated, but now let us make an approximation. Let's first look at the simplest case. Case is when P is 0. Okay, that's the zero momentum solution. Zero momentum will cancel these terms. So I just have two independent equations, and I can see that for p equals 0, and remember E by definition is positive, M is also positive, it's a mass. So the first equation will give us a trivial thing that E equals M, because if P equals 0, then E equals M. So this is not really an equation, it's just a tautology, but the second equation cannot be satisfied by any finite US, right? So the solution to this is actually US is 0 and UB can be anything, okay? Right? Okay, good. So that's just to explain why I call this small, because if P is now not 0 but slightly non-zero, namely if I have a momentum P that is still much smaller than the mass, in fact this is going to be the limit where we can do the non-relativistic limit, right, and develop the Schrödinger equation. Then I get a correction, then US will not be 0, it will be something, but relatively small, okay? But naively, you'd think, okay, what am I doing now is to actually rederive the Schrödinger equation, okay? That's correct, but we'll get a correction to that, okay? We'll get the Schrödinger equation, but we also get a correction, a non-trivial correction. Okay, so how do I see it? First of all, let me not do any algebra, I'm just writing the result. So the result for U sigma, just for the general case, will be that U sigma will be write it like this. There's some normalization factor, and now remember this is a 4-component spinor, and here I have okay, sorry. So it's this, so be more general, and then there's a sigma dot p divided by E plus M sigma, where the state sigma is up or down, so the state up is the spinor 1, 0, and the state down is 0, 1, just the usual SZ eigenstates of the spin half, okay? So in fact this is just a spinor in the spin sector, but it has mainly the first component is dominant, that's what I call the big, okay, that's the UB, and the second, the small component, is of course small by a factor of P over E, or E plus M, but what you have, of course, the expression here must be a scalar, so it's sigma dot P, okay, scalar product with the spin. So what I want to emphasize is that it contains some information about the spin, okay? Contains some information about the spin. via this term. And that's the thing, that if you want to write something that is linear in momentum, because momentum is a vector, it must appear if you want to make a scalar of it, it must couple to the spin, right? So that's the structure of the Dirac equation. It forces the spin into the. Anytime you have something linear in momentum, must come with a spin. Okay? Now, why is that important? Because now I want to let us do or write down the equation for the square of the Hamiltonian, okay, or the square of the energy operator. Okay, we need to erase some things. I think now we can essentially erase this. Okay. So if we go back to these coupled equations, we can in fact, and we just look for a solution to the part of the spinor that I called UB, right? So U sigma was UB, US, and I just look for the effective equation for UB, I get the following equation, E square minus M square minus sigma dot P square times UB equals 0. Okay, that's the equation for UB. Okay, and I want to write it as something that will give me the sorry, wait, is that what I want to do? Yeah, actually, sorry, that's not okay. That's not what I wanted to do. Let me go back. Sorry, I had E minus M UB minus sigma dot P US this, and I had minus E minus M US plus sigma dot P. Sorry that I erased. And now I plug in, I can use this equation to write an expression for US in terms of UB, so it will be down from UB by sigma dot P divided by EM, and then I plug it back into the equation, and I get one equation for sigma dot P square divided by E plus M, and all that multiplies with E. Okay, so that's what I want. Okay, I don't want to multiply by. I can multiply it by E plus M, but I want to actually leave it like this. Okay, let's leave it like this. So this is just for a two-component spinor now. Okay, this is a two-component spinor. All right. And now I want to make the approximation that P is much smaller than E. Okay, in that case, E is to leading order, it's actually given by N. Okay, there are corrections of order P square, but since this term already in the denominator here I want to keep it, but in the denominator I can actually replace E by M, right? Because it's already quadratic in P, okay? So if I keep the orders right, what I get is that E minus M equals, this is, I'm rewriting it as something that looks more like a Schrödinger equation, is 1 over 2m times sigma dot p square ub. Okay, so here I made an encapsulation. Okay, great. So in fact, what I got here is nothing but, it appears like the static Schrödinger equation, and the right-hand side is in fact, it looks naively like it's going to give me nothing but p squared over 2m, right? This would be correct unless, in our case, ub is a spinor. Okay, that's a spinor. And it's a spinor that we chose here a basis where it's actually diagonal in the spin. It's written in the spin basis. Okay. Okay. So this UB, I want to emphasize, this two-component spinor is the spinor that we know and love for a particle of spin half. Okay. We already reduced it to something we are familiar from the Schrödinger equation, and this is what it is, and the m is nothing but a shift of the zero, right? Because the energy is starting. Actually, if you do the semi-classical approximation, is given by m plus p squared over 2m, right? That's the, you know this from relativity, right? This is an approximation, so this is a trivial shift. Okay, so it appears like we just recovered the Schrödinger equation, but not quite, because UB is a spinor, and here I have the Pauli matrices. If you are careful, it turns out that there is a correction to the usual p square if, and that's exactly the point, if you have a vector potential, if you are in an electromagnetic field. If not, so if there is no field, okay, or if you like, for neutral particles that don't couple to electromagnetic fields, then this term is just, so sigma dot p square is just p square, okay? And that's because sigma, you can open this and see that sigma j square is 1 for any j, etc. So you just recover p square. But if you have a magnetic field, okay, electromagnetic field, okay, let's be more general, I have a vector potential, I have a correction, okay, and this correction is going to be relativistic. So now let's see what is the correction, and what can I erase? Yeah, I think, okay, let's, okay, so let's start from this. This is my approximation, but now I want to see what happens if I actually, let me rewrite it here for good measure. Okay, so E minus N and now I have a vector potential and my momentum is shifted into P minus E A. Actually, when I say minus E, I work in units where H bar equals C equals 1. But if I bring back the units, what I have here is E over C. Okay? We'll bring it back later. But bear in mind that there's a factor. This correction will involve a factor of 1 over C, where C is the velocity of light. And if you are talking about relativistic particles, it may play a role, okay? If 1 over C is not infinity, okay? All right, so what do we get? Let's see the punchline. So I want to first introduce a formula. Let me write down the new operator. Sigma dot P square will now become, I'm going to write it slowly, P minus EA. Okay, this is all, by the way, the vector potential. The vector, the vector potential part, the one whose curl is a magnetic field. Okay? I get this times another factor of sigma and another factor of P. And that's the thing. We have to remember that what is A? I'm writing it as an A, but A is actually a function of space, okay? And let's, for simplicity, just assume space dependent, okay? Because the time derivative doesn't come in any way. It is space dependent, and its curl is the magnetic field. Now, because it's a function of R, it does not commute with P. Okay? So you have to be careful with the orders. And in fact, when you open up this thing, you see that you get a term that is just sigma dot P squared, just like before, but you also have cross terms, right? And you also get some correction that it goes like A square, and that's okay, just something that can be compensated with. It's just a constant that comes from the energy of the electromagnetic field. But the most important part is the cross terms. The cross terms are they involve non-commuting objects. So P cross A. So P and A are not commuting. Okay, P here I want to keep as an operator, because once I have electromagnetic field, maybe I should have said it before, this P is no longer a good quantum number, right? It's no longer, because we have a vector potential. It's space dependent, so right? It's not just a good quantum number. Okay. Okay, so P here is the minus I H bar gradient. Okay, or just the gradient. Okay. Now, because of that, I get the correction from this term. I will get the P square over 2M plus something. What is this something? first let me write down a formula. When I have a Pauli matrices times some A and Pauli matrix times B, where A and B are some vectors, okay? This is generally given by, let me just copy it carefully. So the first trivial part is A dot B minus, there's a correction, which is, sorry, there's a plus here, plus I sigma A cross B. Okay, that's an algebraic identity. Okay. All right. Very good. And by the way, so if A equals B, this term is 0. So I don't care about it. But in our case, we also have the cross terms, and this is what will give the correction. So if I apply this formula to the right-hand side, I get that what I called H, which is the right-hand side operator here, becomes P squared over 2m, just the kinetic energy of a non-relativistic particle, minus, sorry, there is, wait. There is this term too, but then there is a term that, let me just keep track of the signs, which you can write as minus I sigma vector over 2m times P cross A plus A cross P, where again P is an operator. Okay? And I miss the factor of E somewhere. Sorry. I, E, and sigma. Okay? Now what is this? If you now remember that P is the gradient operator, and when you change, you have a vector product, you change the order, there's a minus sign. And what you find here is that this term will give you just, with the factor of minus I inside, let me write the result. It will give you a scalar product is E over 2m times sigma dot curl of A. Okay, so to get this, I replace P by the derivative operator, the factor of minus I and I cancel, and that's what I get. And what is this? This is magnetic field, right? And how do we call this term? This is the Zeeman coupling, right? Sigma is really the spin. And the factor up front is, we wrote wrote it as E over 2m because we used h bar equals c equals 1. What happens if I put back the units, the physical units, then I get, I get that this, let me call it, there's a term, delta H, sorry, I want to include the minus sign. The minus sign just suggests that it wants to align with the magnetic field. The spin is in the positive direction. So this delta H is minus G mu, sorry, very important, sorry. Wait. No, fine. It's good. It's good. Yeah, so I forgot something. So let me write it like this: G mu B sigma dot B. But what is sigma? Sorry. So let me do it a little. Sorry that I'm a bit sloppy. It's E h bar over 2mc. This is just taking this and replacing and putting back the h bar and the c. So this is how it looks. Where this factor is known as the Bohr magneton. Okay, so just this factor. It's called the Bohr magneton. And but this sigma is not yet the spin, okay, because it's a spin half. Okay, so if I want to relate it to something that has the angular momentum quantization, so S is actually 1/2 sigma. Okay, so if I want to relate it to the Zeeman coupling, I have to write it as G mu B S dot B. This is the Zeeman coupling that you're familiar with, but G has to be 2. Okay, and this is the so-called G factor. So this analysis from the Dirac equation gives you that the G factor has to be 2. Okay, and if you are trying to derive the same kind of thing from the Schrödinger equation, and in fact you can, you miss this factor of 2. I mean, it appears like just a factor of 2, okay? But that's the correct result. Okay, this relativistic, this relativistic derivation is really the correct way of doing it. Okay, that's what I'm saying, and it has to do with the fact that the spin really appears explicitly in the equation. Okay, it couples to the momentum in a non-trivial way, and you don't notice it without electromagnetic fields, but in a magnetic field, it gives you this G factor of 2. Okay, so that's one thing. By the way, so here I assume that it's just a free particle in free space, and there's an electromagnetic field, but nothing else. If you're doing the same thing for an electron in the atom, and in the atom you have angular momentum, not a linear momentum is the good quantum number. So the same kind of analysis will give you a term called the spin orbit. That couples the spin to the angular momentum.
It's like in
chiral materials like cis
Well,
effect?
actually, in materials, in solid state materials, when you write the Bloch Hamiltonian, which it's not so that you have the same mathematics, but it's not the momentum; it's the quasi-momentum. It has a band structure, and the coefficient here is not just a pure magneton, but it has some effective G factor and all that. Then, exactly as you say, then you get term like this, which is called the spin-orbit coupling. And if it's big, heavy element materials, it's very big and it gives a lot of interesting things, and that's actually topological materials rely heavily on this, okay? But it comes from some analysis like this, okay? In the absence of electromagnetic field, it's actually a coupling of the spin to the orbital angular momentum, okay? Okay, so that's one result. The last thing I want to do, I'll do it quickly, and that's to bring back the question of what is this other mysterious component, or what is this tau? How can we understand it? So one way of relating it to a concrete degree of freedom is to work in a different choice for the gamma matrices. So before I gave you a choice of gamma matrices that satisfies the condition, but I told you, look, we can always rotate them, right? We define some gamma 1, gamma 2, and then gamma 5, and then by multiplication by gamma 5, you can rotate the basis and have a new representation. And it's completely equivalent, and in some cases, it will become useful. Now, the basis we used for this problem where the momentum term is small, the case where the momentum was small compared to the mass, right? In the limit of p much smaller than m, it was useful to use a basis where the main part is diagonal, and the main part has to couple to the m, not to the p. Right? You remember the p, sigma dot p was in the off diagonal. Now we want to choose a basis where it's the opposite, and try to look at the case where we have fermionic particles with zero rest mass, okay? Or very, very small mass. Like the neutrino, that until not so long ago, people were not even sure it has a mass. It's so small. So let me introduce another basis, which is the chiral. This is called the chiral basis for a reason that you'll soon discover. So here I want to choose gamma naught to be actually the off diagonal, and gamma j, where j is the 1, 2, 3, is now also anti-Hermitian, but now we have minus sigma here. Okay, we have something like that. And the gamma 5 is now, but it's not exactly important, but it will be now. So actually we exchanged the roles of gamma 5 and gamma 0. Okay, and now I'm looking for solution of the Dirac equation for a free particle. It has the same structure of before with e to the I px and so on. But now I'm looking for, I'm writing u, the spinor u, which is, remember, that's the positive energy. That's the part that describes particles and not the negative energy state. So I'm writing it like this, and the notations here are RL for right and left, okay? And I'm claiming that it's a choice for a reason, because they are going to have opposite chiralities in some. And what do I mean by chirality? First, let me rewrite the Dirac equation in this basis, and I simply write it as a 4x4 matrix, which has the mass here in the diagonal. Okay, this is minus m times the identity, and here I have sigma dot p, and E times E plus sigma dot p, and here I have minus m, and here I have E minus sigma dot p. And this is acting on our URUL vector. I have the signs right. Okay, that's right, and that has to be 0. Okay. Now you can easily see that the m here, if m is different from 0, I get some coupled equations. Once again, I can substitute one by the other and do maybe some approximation. But now let us see what happens if m equals 0. Then this is 0, it's completely off diagonal, and I get two decoupled equations for UR and UL. And this is how they look. E minus sigma dot p times UR equals 0, and E plus sigma dot p is 0. And there is a very simple solution for that. Let us define a quantity that is called helicity, which is a quantum number that relates to the sign of the combination sigma dot p. So it's a coupling of the spin direction to the momentum. Okay, so it's called helicity because you can think of it as a particle that propagates, let's say, the positive direction and has a spin in some direction. If the product is positive, it's like a screw that goes one way. It's like a helix that goes one way, and this has the opposite. So helicity, the sign, which is the sign of sigma dot p, is UR has positive helicity and UL negative. Okay, so the one that has a positive helicity is called the right-handed particle. Okay, it's where you do this. Okay, you have a helix that is right-handed and left-handed, and they're as long as m equals 0, they're completely independent solutions. Okay, so in this basis, we see that such massless particles should have well-defined chirality. Okay, and their enthalpy particles are going to be opposite chirality. Okay, so the helicity or chirality is playing the role of another spin-like degree of freedom that has physical meaning. It can be measured in the lab. Okay, the helicity is really a physical object that you can measure. Okay, Okay, but of course the definition of what is positive or negative now also depends on, the spin is generally symmetric. You can define up and down arbitrarily, but if you have a magnetic field, let's say you have a magnetic field, you can define the positive sigma or up spin as aligns with the field. Okay, so it's something you can have a well-defined situation, and this solution will have one direction of dynamics for a given sign of a magnetic field, for example. Okay, so you can really measure the helicity, and you can identify and this was done in accelerators. You can identify right movers and left movers, and the zero mass, leave them decoupled. Once you have a finite mass, there is a superposition. It's not a good quantum number anymore, and that's where. And in fact, what happens is that you are going to get some oscillations between the allowed solutions, okay, just like when you have a superposition, and the neutrino oscillations that were observed are exactly that, okay. They actually were the smoking gun measurement that proved that they do have a mass, okay. Although it's very hard to actually estimate, and it's still very low, but it does have a finite mass. That's a conclusive answer. Okay, so I think this is a good time to stop. I said the main things. It's a bit of a crash course. You can, of course, read more about it. And the last thing I want to say that it has been developed by Dirac for, basically getting the marrying together quantum mechanics and relativity. And he did it successfully, and he showed that it's working for fermions. And he discovered the positron. Okay, he actually predicted it before it was seen in the lab. And later that there's anti-particle to any particle, and all that beautiful story. And in the last years, however, we can see this physics in solid state, like in normal laboratories that maybe not so just tabletop, but they cost maybe $1 million and not billions. Okay, that's the difference in the scale of experimental equipment that you use. But because the electrons in solid crystals are described by effective Hamiltonian that is derived from a band structure, you can get materials in which the effective Hamiltonian, or the K, if you like, the K dependence where K is a quasi-momentum, has terms like sigma dot K, where sigma is not necessarily the spin, but it can be an isospin. An example is graphene, which is a crystal where you have two sublattices in a unit cell, and they serve like an isospin. Okay, and the effective Hamiltonian has such terms to very good approximation. It recovers the Dirac equation, however, with velocity of light that is much smaller, of course, by a factor of 300 or something. But it has relativistic dynamics in many senses. Okay. Including the fact that, when it goes through a barrier, there's a Klein paradox and all sorts of nice things, and the chirality also comes in. Okay, so all that you see in solid state as well. Okay, so thank you for the patience and for keeping up to the last lecture, and good luck in the exam. There is, I sent a message, I hope you saw that closer to the exam you can practice all the exams. Nothing will be on the Dirac equation, everything is in the previous lectures, and will be available for tutorial by then, but there's still a lot of time. I still have to invent the exam, unfortunately. Okay, so
תודה רבה.
have a good weekend.
גם לך, תודה.